So hello everyone. So this video basically covers two process scheduling algorithms. First is the first come first serve process scheduling algorithms, and second is the shortest job first process scheduling algorithm. So the main idea of designing this video is to give you the logic of how these two algorithms work. So in lab, we have already seen the working of these two algorithms, and I have also given you the code of how these two algorithms work. However, I've made this video so that anyone who is having any doubt, any trouble, especially in the coding part, can refer to this video again and again and see how exactly these two scheduling algorithms work. So let us start with the first scheduling algorithm, which is first come first serve. So first I will obviously give you a brief introduction about this scheduling algorithm. So as we have already discussed, this scheduling algorithm is used to schedule process in the order of their arrival time. So basically not exactly the arrival time, but the order in which they come. So the process which comes first is allocated the CPU first, and the execution takes place, and then it is removed from the queue. Simultaneously, the second process, the process which comes second in order, will go second. So as soon as you are there, you get the CPU, the process is run, and you exit. So this is one example of first come first serve. So you can see three processes here: P1, P2, P3, with their duration, that is their burst time. So duration or burst time is the same. So burst time is basically how much time the process takes to run. Okay, this is P2 takes let's say 3 seconds, and P3 takes let's say 4 seconds. So the unit can be seconds or milliseconds depending on the question. And now the order. So the order in which they arrive is written here: 1, 2, 3. Means P1 comes first, the order of P1 is first, order of P2 is 2, the order of P3 is 3. Now let's suppose the order was 1, 2 and 3. So in that case, I would be starting off with P3 first because its order is 1. Then I would go with P2, and then I would go with P1. So, however, but in this case, the order is not like that. The order is P1, P2, P3, which is written here. So I will move accordingly. Now, first, starting with the Gantt chart, you can see first process P1 is there. So obviously P1 gets the CPU first. The duration is 24 seconds. So it is given 24 seconds for its execution. So 0, say let's say this is, maybe let me start with 1 only to give you the proper timing. So once it 24, say entire 24 seconds, P1 executes. Now the execution of P1 is finished. Now comes P2. So P2 takes 2 seconds to execute. So again I see, no, P2 takes 3 seconds to execute. The order is 2. So means secondly now P2 will come. So P2 will take 3 seconds. So again P2 takes 3 seconds. So I will add 3 with 24. So it will go to 27. And then P3 comes, next order is of P3. P3 come, duration is 4 seconds. Then again 4 seconds is add, and P3 is run. So again in this case, if I add 27 and 4, I would get 31. Okay, so this is the Gantt chart here. Now I will be calculating the waiting time and average time. Now in all the scheduling algorithm, our main aim is to calculate the average waiting time and turnaround time of the process. So in order to calculate the average waiting and turnaround time, I need to first calculate the waiting time and turnaround time of each and every process, each and every individual process. Now the formula to calculate first the turnaround time is completion time minus arrival time. So this is the formula of the turnaround time, and turnaround time is the amount of time that is taken to complete a process. So the complete time that a process takes is referred to as the turnaround time, and waiting time is calculated by this formula, turnaround time minus burst time. Now arrival time and burst time are already given to you in the question. Okay, they will be always given to you, like in this case the arrival time and the burst time is given. Completion time you will get from this Gantt chart. You will have to draw the Gantt chart, you have to find out the completion time, and when you get the completion time, arrival time, you find the turnaround time. This turnaround time is used to calculate the waiting time. So this is the entire sequence here. Now I will be calculating the turnaround time, waiting time of each and every process. So if I start with, let's say, the turnaround time. So turnaround time of process P1 would be its completion time. So P1 is completed at 24 seconds. So 24 minus arrival time. So arrival time of P1 is 0. So arrival time of all process here is 0. So which indirectly means that in this case the turnaround time is equivalent to the completion time, because the arrival time of all process is 0. So that way I would get the turnaround time of each and every process equivalent to its completion time, which is again for P1 it's 24, for P2 it's 27, and for P3 it's 31. Now the waiting time. So the waiting time for P1 is turnaround time, that is 24 minus burst time, which is here in listed here, which is again 24. So that is 0. So means which means P1 is not waiting, which is true. P1 gets the CPU as soon as it is there. P2 waiting time is turnaround time, which is again P2's turnaround time is 27 minus its arrival time, that is 3, that makes 24. And P3 is turnaround time is 31 minus is burst time. So burst time again you see here is 4 minus 4, which gives 27. Okay, so these are the waiting time and the turnaround time of all the processes. Now the average would be, again we will be adding these three values divided by 3. So 24 plus 27 plus 31 divided by 3, which would give me the average turnaround time. And average waiting time would be 0 plus 24 plus 27 divided by 3, which would give me I think 17. So this would be the average waiting time of all the process. So that's how you will be calculating the average waiting time and average turnaround time. Now the thing is, logical wise, numerical wise, we are able to do this, but when it comes to coding, so there the main problem occurs. So I will be explaining you the implementation of the first come first serve in C language. So the program starts here. So this is the program, okay, the C program for the first come first serve scheduling algorithm, and this is the algorithm written here. So the algorithm says first we need to input all the processes along with their burst times, then we need to find the average waiting, then we need to find the waiting time of all the processes, and as first process that comes need not have to wait, so the waiting time of first process would be 0, which we have already seen that in this case the waiting time for first process was 0. Then for other processes we would be calculating the waiting time based on this formula. The turnaround time would be calculated based on this formula, and then finally the average waiting and average turnaround time. So this is the algorithm. Now we'll see how to write a C code, C programming code using this algorithm. Now starting off with the main function. So this is the main function where your execution will start. Now suppose I have three processes with me with the ID 1, 2, 3. So P1, P2, P3 are three processes with me. Now next step says int n is equal to size of processes divided by size of process, 0th process. So n says that the size, what is the size of each process divided by the size of individual process. So again, just see that the size of processes here, this is an integer number here. Okay, so this is an integer, and let's say integer holds 4 bytes inside the memory, and here there are 3 numbers here. So this would be 4 into 3, that is 12. Now what is the size of any one process, any one integer value here? That is 4 only. So the answer would be size of processes, this would be 12 divided by this value, that is 4. So 12 by 4, that would be 3. So n would be 3. So this is one way of how you calculate the value of n, that is number of processes. If you want, you can directly take the value from the user also, input the value of n from the user also, that is also one option. Then here the burst time of all the processes are listed. So 10, 5 and 8 are the burst time. So the burst time of the process is 10, 5 and 8. Now first, what is given? That first you need to find out the average waiting time. So this is the function given here, average waiting time, which takes this processes, the n value and the burst time as the input. So directly the call will go to this find average time function, which is this. So this is the function which calculates the average waiting time. So the average waiting time, we can see some integers listed here. So this is an array. This is the waiting time array, turnaround time array. This is the variable, integer variable, which has total waiting time equal to 0 and total turnaround time equal to 0. Internally again we have 2 more functions here, find waiting time and find turnaround time. So let's first go to the find waiting time function. So find waiting time function is again here. Now what this function is doing, this function is calculating the waiting time of all the processes. So as we said already, we have seen that the waiting time of the first process would be 0. So accordingly we have initialized the waiting time of first process as 0. Now we need to calculate the waiting time of other processes. So therefore in this case the value of I will start from 1, because for the 0th process the waiting time is already 0, that is calculated here. Okay, so we will start I from 1. So we say that the waiting time of each process is W, waiting time of ith process is burst time of I minus 1 plus waiting time of I minus 1. Okay, so let's see this with an example. So we had this input, we have 10, 5, 8 as the burst time, right? And we have these 3 process P1, P2 and P3. So waiting time for the first process is 0. So waiting time of this process is 0. Now when I is equal to 1, so waiting time of first process will be the burst time of 0th process plus the plus the waiting time of the 0th process. So this is burst time of 0th is 10 plus its waiting time. So 10 plus 0 is 10. So here the value come tens. Again I equal to 2 pay, waiting time of 2 is equal to burst time of 1 plus waiting time of 1. So burst time of 1 is 5, waiting time of 1 is 10, which makes it 215. So because internally that's how we write the algorithms. So internally the function is indexed from 0, 1, 2. So this is the indexing, right? So 0th index has the waiting time I equal to 0 pay 0, I equal to 1 pay we have 10, and I equal to 2 pay we have 15. So we have 10 and 15 accordingly. So that's how we have now calculated the waiting time of all the process. Now comes the turnaround time. So if you go back and see, waiting time is already done. Now we are into the turnaround time function. So the turnaround time function, which is this, now how we are doing the calculating the turnaround time by using this formula. So see, for I equal to 0, turnaround time of 0th process is the burst time of the 0th process plus the waiting time of 0 process. So turnaround time for 0 process will be its waiting time, that is 10 plus that burst time plus its waiting time. So 10 plus 0, that is 10. So here the turnaround time is 10. Again, turnaround time for the first process is burst time of first process plus the waiting time of first process. So turnaround time would be here burst time, that is 5 plus 10, that is 15. So again it is 15, and similarly for the second process would be 8 plus 15, which makes it to 23. So that's how we have calculated the turnaround time of each and every process here. So this function is used to calculate again the turnaround time. So we can see that now we have the waiting time. This is the process ID. The waiting time we have the turnaround time. So these two functions are completed with their execution. They have completed their execution. Now we need to display. Now what we want to display the output. Now this is printf statement is just to display the output in a particular format. So your output will be something like this: P1, P2, P3 in a tabular form, and then you will be having burst time written here, waiting time, average time, something like this. So a table of this form, this table will be shown with these four things will be shown here in the output. So this is just, these statements are just for the output. So we'll have the processes. These are the heading processes: burst time, waiting time, turnaround time, and that's how you will be displaying. And these two lines will calculate the average waiting and turnaround time. So now you can see that in this array, TAT array, we have the waiting time of all the process, and similarly the WT array has the waiting time of all the processes. Now what we will do is we'll start a loop, and we'll you can say index by index take each and every value of the turnaround time and the waiting time. So let's say if I have an array which has the value maybe 10, 15, 20, so let's say 21, something like that. So what I'll do is, so these all are the let's say P1 waiting time, P2 waiting time, P3 waiting time. I started an array. I picked the waiting time of P1 and add it to a variable which is total WT. So total WT, you can see, is initialized to 0 here. So it is initialized to 0. So what happens, how exactly the waiting time is calculated? Total waiting time is equal to total waiting time plus WTI, right? So when I is equal to 0, so and total waiting time is also 0, so first value is calculated by using 0 plus waiting time of ith process, which is 10. So it gives me 10 value. Now the total waiting time is 10. Again, when I is equal to 1, what happens? Total waiting time would be earlier waiting time, which is 10, plus the waiting time of the first process, which is 10 plus 15, because now this is the first process, and I get value here 25. Now again, now the loop will go on. I equal to 2 pay, I'll have total waiting time is equal to here the previous waiting time, which is 25, plus the waiting time of this process, that is P3. So that's how again the entire loop will go on, and I will get the final waiting time in this total WT array. So let's say the final waiting time is this 45. So total waiting time is 45. So I would be dividing it by number of processes, let's say 3 here. So here in this case, you can see these two lines are written to calculate the final average value of waiting time and turnaround time. of all the processes. So that's how you calculate the average waiting time and the average turnaround time of the individual process. So you can see here, this is the average waiting time, this is the average turnaround time, and now you have printed both the values. And finally, what I got as an output, the output here you can see includes everything. The table, you can see one table with all the details are listed here. Second, the average waiting time and turnaround time of all the processes. So these are the things which are listed here to calculate the average waiting time. Now this was the first come first serve scheduling algorithm. Now let us move to the second scheduling algorithm, which is the shortest job first, and we'll be discussing the non-preemptive version of that. Now before going into the preemptive and non-preemptive part, basically what do you mean by the term preemptive and non-preemptive? So preemptive basically means whenever the process is executing inside the CPU has no longer, the CPU cannot stop the execution. The CPU can obviously stop the execution of that particular process in case of preemptive. So in case of preemptive, what CPU can do? CPU can stop its execution. Okay, now the question comes, why the CPU would like to stop any process from executing? Now there could be many cases that, let's say a process is executing, there is a process P1 which needs, let's say, maybe 120 seconds to execute, and there is yet another P2 which needs only 2 seconds to execute. Now let's say P1 is executing and automatically P2 process comes, or any other important process comes which needs immediate attention and needs the CPU immediately because it is on high priority. So whenever we have high priority processes coming in, so obviously we need the CPU at that particular time. So in that case, what CPU would do, CPU will halt the execution of this process and immediately start executing the P2 process. And once the execution is completed of the P2 process, it can again switch back and resume the execution of P1 process. Now here one very important thing, two very important points needs to be considered. One is the problem of starvation. Now the advantage of this preemptive version is that, let's say if there is one process who is running and the second process needs very less time, I can stop this process and continue my execution with this process. Now in this case, starvation will never occur because this process P2 will get the CPU for its execution, whereas under the non-preemptive version, what happens is you cannot halt the execution of P1. So P1 will execute till 120 second and no other process, or let's say, could come and halt its execution. So in that case, the second process would suffer from the problem of starvation, means it is not getting the CPU for its execution. CPU is completely busy with the execution of the first process only. So there comes the problem of starvation. So under the preemptive version, we don't get the problem of starvation because again the CPU, we have the control that CPU can halt the execution of any process and start the execution of some other process, whereas under the non-preemptive version, the CPU will have to execute the complete process, and once the process completes its execution, then only it can again refer back and go with the second or any other process. Now second important part which needs to be discussed here is that what is context switching. Now context switching means, suppose again I have P1, again P1 takes 120 seconds, P2 takes 2 seconds to execute. Now let's say I am executing P1, and let's say after 60 seconds P2 comes and I need the CPU here. So what I will do is, since P1 is already P1 has already run till 60 seconds, what I need to do is I need to save the state of P1, so that when because it is already run for 60 seconds, so I need to save the state of P1, I need to load the state of P2, and now P2 will run for 2 seconds, and after it is completed with the execution, I need to again load the state of P1 now. Okay, because now the execution will start from 61st second, not from again from the 0 second. So this will not happen. Execution will start from the 61 second only. So that means what context switching is doing, it is saving the state of the old process whenever a new process comes in and needs the CPU. So I'm saving the state of the old process, and then after the execution completes, after the new process execution gets completed, I load the state of P1 again, and P1 can again start with its execution. So this is the so this is what the context switching is all about. So two very important topics here, or let's say two very important concept here, are the starvation and context switching. So we'll be looking into the non-preemptive version of the SJF, which is the shortest job first algorithm. So in the shortest job first algorithm, the criteria is to look at the arrival time first and then the burst time of a process. So so the algorithm firstly says that the any process which has the shortest burst time will be executed first, so that again there is no problem of starvation. The maximum, the you can say the maximum scope that we could have here is, let's say the small process gets executed first, and then obviously the larger process can come and take hold of the CPU. So the process with the smallest burst time obviously gets the CPU first, but arrival time is also taken into consideration. So obviously the process when they arrive, so that is also taken into consideration here. So let's say I have the table here with the process ID, arrival time and the burst time. Now what I plan to do is I need to prepare a Gantt chart for the execution. Now let me start with a Gantt chart. So I start with time 0. So at time 0, now if you see the table, the arrival time is listed and the burst time is listed. Arrival time is 1 2 1 4 and burst time is 3 4 2 4. Now the Gantt chart says at time 0, arrival time 0, is there any process? So I can see there is no process which is arrived at 0th second. So from 0 to 1 I have no process to execute. At 1 second I have two process, P1 and P3. So I have P1, I have P3 with me. Now what I do is first I have taken into the consideration the arrival time. Okay, and then I will look at the burst time. So I have P1 and P3 here. Now the shortest burst time is of P3. So what I'll do is I'll write P3 here, and P3 will execute for 2 seconds. So for 2 seconds it gets executed. So and P3 is done with the execution here. So P3 completes its execution. Now at 3 seconds, how many process I have? P1 I already have. I have P2 also now. So P2 is also there. So I see P1 and P2 both are there, but the shortest burst time is of P1 only. So P1 gets executed. Now P1 is written here and it gets executed for 3 seconds. So again it gets executed for 3 seconds. So again P1 is completed. At 6th arrival time I have P2 also, and now I have P4 also, because arrival time of P4 is 4, so it already arrived at 6 seconds. So now again out of P2 and P4 I see both has the same burst time. Okay, but Now if you have the same burst time, what you can do is you can look at the arrival time, which process arrived first. So this could be like the first come first serve scheduling algorithm, that the process which comes first gets the CPU first. So we saw that P2 came first, P2 arrived first. So in this case I will execute P2 first, and P2 will be executed for 4 seconds. That means till 10 point, so till 10 seconds. And then after P2 completes its execution, I now have just P4 left. So now P4 completes its execution for 4 seconds. So this is the complete Gantt chart here for the shortest job first, and that's how you calculate the arrival time. Burst time is already given to you. You calculate the completion time, turnaround time, and waiting time. So similarly the same formula is there as we saw in this particular version of first come first serve, that the waiting time is the turnaround time minus burst time, and the turnaround time is completion time minus arrival time. So turnaround time would be completion time minus arrival time. So turnaround time for P1 is completion time of P1, that is P1 got completed at 6 seconds minus its arrival time, that is 2. So this is 2. So turnaround time of P1, so let me check turnaround time of P1 is okay 5. So there is some mistake. So completion time of P1 is 6 here, and the arrival time, okay my bad, arrival time of P1 is 1, not 2. So you can see here, so that's how this is 5. 6 minus 1 is 5. Okay, similarly turnaround time of P2 is what? The completion time of P2. So this is 10 here minus the arrival time of P2, which is 2. So this is 2 and this gives me 8. So again the turnaround time of P2 is 8. And waiting time would be what? Waiting time would be the turnaround time minus the burst time. So waiting time of, let's say, P1 process is turnaround time, which is 5, minus the burst time, which is 3. So 5 minus 3 is 2. 8 minus 4 is 4. 2 minus 2 is 0. So that's how you calculate the turnaround time of all the processes. Now next important thing is the coding part, that how you need to code and run the shortest job first non-preemptive version. Now again quite the logic, some input and output is obviously the same here. So you can see this is the code here, the main function. So under the main function, what all I have several declarations. I have one array here, which is the burst time array. So this array is of the burst time. One array I have made of arrival time. Okay, this array is of the start time. This is the finish time or the completion time. This is the waiting time. Okay, and then finally I have the turnaround time. So again I have multiple arrays that are already declared here, and then I have two integer variable, total turnaround time and total waiting time and total turnaround time. So two integer values listed. Then we have average waiting time and average turnaround time, and then we have one array which is the process number, which holds the process number, and there is also one array that holds the time. Now exactly how we'll proceed? First we'll input all the processes, the number of processes. So these are the normal input statement. Here the process number of processes is taken. Here the process name, arrival time and burst time of all the processes are taken. Now next part says what? Now in this part what we do is we do the sorting. Okay, we sort the entire input on the basis of their burst time. The process which has the smallest burst time will run first as per the shortest job first. So we'll sort the entire processes in ascending order so that the process with the shortest burst time comes first and is executed first. So let's have first some input. So maybe my input is this. I have P1, P2, P3, P4 process with me. Then arrival time and burst time of two processes are written. So let's say the arrival time of P1 is 1, P2 is 2, P3 is 1 and P4 is again 4. Next, the burst time of P1 is 3, of P2 is 4, P3 is 2 and P4 is again 4. So this table basically denotes the arrival time and burst time of the four processes, and we'll take the input from the user. Now, and obviously we have numbered it 1, 2, 3, 4, but indexing would be from 0, 1, 2, 3. Now let's see these two loops here first. I have ith loop and I have jth loop. Now many students were facing problem with the logic of this particular scheduling algorithm, that is the shortest job first, and especially at this particular part. Now let's say I start the first loop, which is the ith loop. I say I equal to 0. I would be less than n, so n is here 4 and I plus plus. Similarly, I have j equal to 0, j would be less than 4 and j plus plus. So first I is 0 and j is also 0. Then I move to this line. I see burst time. I say burst time of ith, that is 0, is less than burst time of again jth, which is 0. So again in both the cases the time is same, that is 3 is less than 3, which is not the case. So again the loop is not executed, this particular loop is not executed, and the value of j, again the compiler comes here and the value of j is incremented, j is 1 here. Now what happens, again a comparison is made and I remain 0 only. BT0 is less than BT1. Now in this case just check, BT0 is 3 and BT1 is 4. In this case this is 2. Now the internal loop will occur. So you see this is the sorting, a normal sorting by swapping them. So we have used a temp variable to swap the arrival time, the burst time and the process ID, because we have three things with us. We have the process ID, arrival time and burst time. So that's how we'll be sorting all these three with the help of a temporary variable. So this logic is obviously of a normal sorting algorithm. Any sorting algorithm that you apply, the normal swapping is there. And since the process ID here is a character, so we use the strcopy function for its swapping. So we need to swap is using this particular function. So these three swaps the process ID, these three swaps the burst ID and these three swaps the arrival time. So in this case, if the burst time of the first process is greater than the second process, we need to swap these two processes. Now what happens once we swap these two processes, the new table would be like this. We will have P2 here, we'll have P1 here, then this would be 2, this would be 4, this would be 1 and this would be 3. Let me just cut it. This would be 3 because we have swapped the 0 and 1 process, so we have swapped their complete value. So process IDs have swapped, arrival time has swapped and obviously the burst time is also swapped. Now after this what happens, we check BT0 is less than BT2, J value is again incremented. So once the swapping is done, J value is again incremented. You see BT0, which is 4, is less than BT2, which is 2. That is not the case. Then you see, then j value is again incremented. bt0 is less than bt3, so 4 is less than again 4, which is again not the case. So now I is incremented, I equal to 1. Now I equal to 1 में the j would again start from 0. So I equal to 1 and j is 0. I check that bt of 1 is less than bt of 0. So burst time of 1 is 3 and of bt0 is 4. So this is true again. Then again a swapping is done. So we again swap the value p1 and p2. So again this would be p1 only, this would be p2. Okay, let me just erase it and write it correctly. So let me just erase it again. So this would be p1, this would be p2, and this would be 1, this would be 3, this would be 2, this would be 4. So this is the revised table here. Now next I again increment the value j and I write bt1 is less than bt1. So again this would be false. Again j is incremented. We see bt1 is less than bt2. Is it true? So bt1 is 4, it is less than 2. So that is not the case. Again I check bt2 is less than bt2. Sorry, bt1 is less than bt2, so 4 is less than 4. This is also not the case. So we have again, now what will happen is I value would be incremented. Let me now again erase the value. So I was initially 1. It was obviously for 0, then it is 1, and now it is 2. Now I equal to 2 pe I'll again check for j equal to, from j equal to 0 till 1 2 3. So first j equal to 0 pe I check that bt of 2 is less than bt of 0. So just see bt of 2, which is this 2 is less than 2 is again less than 3. So this is true. Okay, so again I'll swap the 0th and the second process. So this would be p1 and this would be p3. And again I will swap the arrival time and the burst time also. So this would, the arrival time is 1 1 only, and this would be 2 and this would be 3. The swapping is there. So again now I check b2, 2 is less than b2 of 1. So b2 of 2 is what? 3 is less than b2 of 1. This is also true. Again I will swap these two process, that is this and this process. So let me now erase it. So now it would be what? This would be p1, this would be p2, this would be 1, this would be 3, this would be 2, and this would be 4. So again after the swapping I see if b2 0, if burst time of 2 is less than burst time of 2, this would be false. If burst time of 2 is less than burst time of third process, that is 3 is less than 4. Now again in this case you can see bt of 2, that is this, is less than the bt of 3, that is this particular value. Now in this case again the swapping would be done, so you will get a revised table here. Now you can see that the final table, if you start computing in this way, so the final table would be this only. Okay, after the final, you complete these steps also, and you will get the final table would be this only. I'm not getting into too much details of the execution, otherwise it would be completely haphazard. So even if you go ahead and now increment the value of I equal to 3, no more changes would be there. No changes would be there. Even for j equal to 2 and j equal to 3, there was no changes. There was only one change when j was equal to 1. So this would be the final table after all the computation. After all these two computations, you will get this particular table as the final value. And this is just for the printing, for you to see the what would be the final state value. This is just for the printing. So we can skip this and we can come directly to this part. Now the final table, let me first write down what the final table was. So the final table was P1, final table was P3, P1, P2 and P4. And this, the arrival time, the burst time. Now if you see here, after the sorting, after completing the sorting, I got this as the final table, which means now you can see the burst time here are in the sorted order, 2 3 4 4 in the ascending order. Now I can directly execute. I have the ascending, the table in the ascending order, in the you can say in the order in which the smallest process comes first as per the shortest job first logic. So the idea for this algorithm was to get a sorted table as per the burst time. Now I can directly calculate my waiting time, the turnaround time, the finish time from this table itself. Now how the logic is here. Now this logic, it computes the waiting time here, the waiting time, the finish time, the turnaround time of each and every process. Now how that is done? Now we run a loop here. So for I equal to 0, so for I equal to 0, I have the st0 is equal to at0. That is the start time. I have multiple things. The start time, I have the waiting time with me, I have the finish time with me, and finally the turnaround time also. So these are some values which I have with me. So you see the st of 0, that is the start time of 0, is it's the arrival is equal to its arrival time only, so which is 1. Next, uh, waiting time of 0 process would be, you just see the loop. Waiting time of 0 is the st of 0 minus at of 0. So waiting time of 0, it's the start time minus arrival time, which is 0. The finish time of 0th process, it's the start time plus the burst time, that is 3. And the turnaround time is the finish time minus the arrival time, that is 2. And similarly, if you calculate for P1, now for I equal to 0, this was the formula, otherwise we need to use this formula. So for I equal to 1, what I do is I write st1 is equal to ft I minus 1. So that is the start time of every process is equal to the finish time of the previous process, which is true. So we know that in shortest job first, the arrival time, the start the time at which the process starts executing, a next process starts executing, will be equivalent to the finish time of the previous process, because we are dealing with the non-preemptive version. So under the non-preemptive version, if one process completes the execution, then only the second process would go ahead and start with its execution. So in this case, the start time of one process is equal to the finish time of the second process. So here the start time of the ith process is equal to the finish time, that is 3. So at this particular time, the first process starts executing. Now the waiting time. the waiting time of one process is its start time minus its arrival time. So again, waiting time here in the case of shortest job first would be that first there is one arrival time, that the time at which the process arrived at the ready queue, and the start time is the time when it gets the CPU. So the waiting time would be the difference of the two time, that when the process is there in the CPU and the time when it gets the the waiting time would be the time at which the process is there in the ready queue and the process gets the CPU. So the difference of these two time, the start time, that is here the time when the process gets the CPU, minus the arrival time, that is the time at which the process is there in the ready queue, is its waiting time, because the time at which till which it is waiting for the CPU. So this is STR1 minus 81. So this would be 3 minus 1, that would be 2 here. Now turnaround time for the first process is its finish time minus its arrival time. So this is again pretty much self-explanatory. Turnaround time is the time that we calculate, that how much time the process is spending within the CPU, how much time the process takes for its complete execution, okay, till the time it arrived. So we say, because since it's a non-preemptive version, so again the finish time would be 1 only, because the process finishes whenever it starts, it finishes. There is no longer a case that process will again be let's say picked for the execution. So here this would be ft1 minus the 81. So before that, okay, we forget to calculate the finish time of the process. So finish time of the process is start time plus the burst time. Again, start time plus the burst time would be the finish. So start time is the 3 plus the burst time, it is again 3. So 3 plus 3, this is 6. So the value here is 6, and accordingly we calculate the turnaround time, which is 6 minus arrival time, that is 1. So this is here 5. So we have the value here as 5. So similarly you can compute all these values here and get the start time, waiting time, the finish time and turnaround time of all the processes, and then we'll calculate the total waiting time and the total turnaround time. Again, for this we have already initialized these two integers as 0, and these are the two arrays. So the technique which we use to calculate the total waiting time in the first come first serve, we'll be using the same technique here to calculate the total waiting time and the total arriving time. And then we need to calculate the average waiting time and average turnaround time. So average waiting time would be, again we need to divide the value by the number of processes we have, divided by n. So you can see here the average waiting time, and then after that also one very important thing here, the average waiting time and average turnaround time, ATA, these two values are double. Okay, the value here is double, means the data type here is double, because we will have integer values involved. Okay, whereas the value total waiting time and total turnaround time was integer. So here what we are doing, we are converting an integer value to a double value, and the result would be obviously double. So that's how we are using, we are casting it, we are using the double variable layer to again for the conversion of one data type into another data type. And in this particular case what we are doing, we are just printing the values here. So you can see the process name, the arrival time, burst time, waiting time and turnaround time here. And the value here would be again this is the process number, the average time of all the processes. So again this particular table will be there. So the table which you see here, the entire table would be printed again, and then the burst time, we have the waiting time, turnaround time, and then finally you print the average waiting time and the average turnaround time. So that's how you again create the algorithm of the shortest job first process scheduling algorithm. So this is how the working of the entire shortest job first scheduling algorithm. So you can see here all the things, the sorting. Firstly, if I just quickly recall the shortest job first scheduling algorithm, what exactly we have done is, the idea for the shortest job first was to sort the process in the ascending order, because as per the logic of the shortest job first, we execute the process which has the least burst time first. So any process which has the least burst time is executed first. So that's why we plan to sort the entire processes in the form of in ascending order. So this was the complete logic here. And because obviously whenever we sort the burst, we need the less burst time at the top, so we need to obviously swap the details, the test details of the processes also. That means the arrival time also, the process id also, we need to swap all the details of for all the process. So that's how we are doing it. We are swapping the arrival time also, we are swapping the burst time also, and finally we are swapping the process id also, so that we have all the information intact of all the processes. And then after sorting the algorithm, after sorting the processes as per their burst time, we what we do, we calculate the waiting time, the finish time, the turnaround time of all the processes. So you see here, the waiting time of the process is equivalent to the start time minus the arrival time, because again waiting time means the time it is waiting, the time that it has spent waiting to get the cpu. So that would be the time that has actually it has spent in the ready queue, minus the time that its execution has started. So that's why start time minus the arrival time. And the finish time is obviously the time from which it starts, it is there in the cpu, and plus how much time it needs to with for its completion. That is the start time minus the start time plus the burst time. The turnaround time is basically how much time the process spends in its execution. So the turnaround time is the finish time minus the arrival time, that total how many time the process obviously is taking time to run the complete with the complete cpu. So these are three very important things. So how much time the process takes for its complete execution. And this was the non-preemptive version of the shortest job first. Obviously non-preemptive version is bit easy as compared to the preemptive one. uh, if we had the preemptive version of the SJF, then things would have been different. In preemptive version, obviously there could be a case that P2, we need to stop the execution of P2, and let's say any other process, maybe P5 process comes, and then again after its execution, I again start the execution of P2. So in this particular case, the values of the completion time, the turnaround time would be different, because in this case P2 will be completed at this particular time, not at this time. So again multiple things would change in that case whenever we have the preemptive version of the shortest job first, and accordingly the algorithm and all the equations will change in that case, because again we'll be halting the execution of the process and again starting the execution of some other process. And the first come first serve, the first come first serve algorithm is always non-preemptive. It is there is no preemptive version of the first come first serve algorithm, and it is by far one of the most easiest algorithm which can be executed and which can be implemented with the programming languages. So this was in this particular lecture we discussed about two scheduling algorithms. the first come first serve as well as the shortest job first scheduling algorithms. In the next lecture we would be discussing about the two more scheduling algorithms. First is the round robin scheduling algorithm, and then next would be the priority queue scheduling algorithm. So we'll be discussing the coding part, that how to exactly code in how exactly you can write a C programming code of these two particular scheduling algorithm, because you people were facing a lot of problems while writing the code and you were not able to get a proper explanation of the code. So now you can refer to this video again and again for the explanation of the logic of all these algorithms which we'll be discussing, all the process scheduling algorithms which we'll be discussing. So okay,